to my computer and saw it, but yeah, I'll try it afterwards. So yeah, as Victor said, this is collective work at Roblox. I'm Iñaki, and this work together with Dario, Tijmen, Eloi, Will, Charles, Ian, of course, Victor, Morgan, and Kiran. And I'll talk to you about how to animate facial avatars, so avatars, the faces from audio and video, with the goal of having a strong compute requirement. Since we are running this now in Roblox, and Roblox is aimed to be used on any device, and kids might use it in devices as maybe 8-10 years old. So our system produces FACS, which stands for Facial Animation Coding System. And yeah, as I said, it runs on real time and can be run on any avatar or any rig that is compatible with FACS. The goal is, so it needs to be robust to any real-world requirements like camera motion, occlusions, hard lighting conditions, and also noises in the case of the audio input. And as I said, we derived the animations from audio and video into different separate streams. The video stream takes obviously frames, and we call it V2C, and produces both health tilt and expressive animations from mouth region and from the upper side or eyebrows and eyes. While the audio stream is in charge of lip sync and also produce an additional signal, we see it alpha, which tells us if there is some kind of voice activation. And it's used in the mod mix, which basically blends the outputs, the FACS outputs from each of the two subsystems. So let's deep dive into the video to animation. Here you see the architecture for video, which takes frame by frames and outputs FACS for each frame. At the core of the system is BaseNet, which is a multitask network, which produces landmarks, FACS, head pose, and face probability. And this is a very, very small network. If there is enough compute budget, then we run an additional network, Hyphenate, which produces like FACS with better quality. Then to do that, we use the landmarks predicted by BaseNet to do a very tight crop for more efficiency. BaseNet also needs a crop, so we run what we call face propulsion network. It's just like two first stages of an empty CNN, and we just run it basically on the first frame, because once you detect the face, BaseNet is in charge of using the landmarks from the previous frame to align the face and be very efficient. So this is the internal architecture of both BaseNet and Hyphenate. It's an encoder, decoder architecture. The encoder is based off MobileNet V2 blocks, but making them like small, and we'll see some details on the resolution later. And then the decoders, here we see the decoder for FACS, is basically a set of causal convolutions, only using like past and current frames, followed by an LSTM and a fully connected layer. Here's some details to get an idea of how large these networks are. For instance, BaseNet has just an input resolution of 65 by 65, means that you have to derive all the information from that small resolution. And this translates in just like 5.23 multiply accumulates. If you don't know what multiply accumulates, you can estimate that there are like two times flops, so that will be like 10 million flops. In comparison, like if you compare to MobileNet V2, which we got inspired, the standard MobileNet V2 is 300 million max, right? So we are like 60 times smaller in the case of our fastest network. And yeah, the decoders are much, much smaller. So now the question is, how do we train this network using supervised training? because given a real image, there's no correct definition or exact definition of what the facts weights for it are. So the solution, immediately the solution is use synthetic data. This has also the advantage that you have perfect labels. And in addition, you can get a perfect, like a nice distribution in terms of gender, ethnicity, etc. The problem with just using synthetic data is that the features obtained by training with synthetic are different than the features you get when you run inference on real videos. It was what I call the domain gap problem. So to address this problem, we train our network in 2 stages. First, we train the encoder just using landmarks with a combination of real and synthetic data. We used a positional loss in the landmarks and a consistency loss using pairs of images with affine transform, and this unsupervised loss, we don't need annotations for that. And then we freeze the encoder, so we don't change the weights. The encoder is already able to have a representation that is valid both for synthetic and real data. And we freeze the encoder, and then we train the decoders. In the case of facts, we use a positional loss. We use a velocity loss, which allows us to have a smooth but also dynamic predictions. And we add a regularization term on the acceleration, which further decreases jitter. Now, I'll go into the audio to animation network. Basically, we take audio, we convert it into a MFCC representation, and we fit another convolutional network, very, very small network. And as I said, it produces the facts for the lip region or for the mouth region and voice activity detection. The goal of this network is to generalize across different users, be robust to audio noise, and has to be also like light. Again, like encoder-decoder architecture, our encoder looks very much like the decoders of the video part, as they're convolutional layers followed by LSTM and fully connected layers, and then the decoders for both subsystems, they are a fully connected layer that projects into a smaller space towards the LSTM and a fully connected layer. The LSTM is where most of the compute happens. I'm not putting here the values of the max, but this network is even smaller than the decoders of the video part. So mainly means that we can use this model almost for free. And this allows us to have lip sync without needing to have high resolution for video. Which if you will want to have details on the lip region, you will need more resolution and a more expensive network, or another possibility would be to have like a crop, like a specific network for the mouth. So a first idea to train this network would be, okay, we have a set of we need to generalize to different people, so we get a set of speakers and we train end-to-end. That was some early experiments. But what we found out is every person articulates their mouth differently, which leads to different labels. Now, what happens if you train something like that was that the predictions tend to be over smooth and not so dynamic, so to say. And we found out that if you train on a single speaker, then the predictions are much better, but then you don't generalize. So our solution to that was again to train in 2 stages, train the encoder. We trained the encoder on a phoneme classification task, so we get like a large data set of audio with different speakers, and we have phoneme annotations for those transcripts. And so the intuition is that phonetic speech has high correlation with the visual speech units called VSIMs, and then the representation that is learned there is closer to the facts we'll predict later. Now, so in the second stage, again, we freeze the encoders. We did for video. And in this case, it's not too biased. And we train for just with a single speaker, right? And then we freeze the encoder to avoid biasing towards that speaker. So we don't lose the generalization to multiple speakers. And we train for facts and activity detection. Again, for facts, we use a positional loss and a velocity loss. And the activity detection is basically a classifier cross-entropy loss. Finally, once we have the two pieces, we need to mix them, and we just do with some linear blending. So if no one's speaking, alpha is 0, and all the output predictions come from video. As someone starts speaking, alpha reaches 1, and then we start mixing, and we have like a linear combination between the shapes, depending on which shapes are combined in different ways, have different weighting parameters. I wanted to do this.
Tracking video and voice together makes our system very robust to occluders. So for example, my mouth region is occluded from the video. You can see that the lip sync on the avatar is still working with my voice, whereas the rest of my face, like the eyebrows and eyes, are tracked from video. And when the occluder goes away, the system is able to capture both the emotions and the lip sync seamlessly.
Okay, my idea was to do this with the phone. I'll try it afterwards, and if not, please stop me at the corridor and I will show you on my phone. So some implementations we did which were very important to us, they're on 3 pillars like pre-training. So basically, how do we design the network? Basically, input resolution, number of layers, depth per layer, like making them very small. We also used unparalleled convolutions to control the future map. We did post-training, basically fusing layers, this is standard. And then in runtime, our goal, so our models are aimed to run on CPU. This is because it's easier to distribute on multiple devices that we have. We consider and try GPU. The reason we didn't go is it's harder to support GPU. There's more variability across the hardware, but also we found out that our models are so small that they tend to run slower on GPU, mostly because of memory bounding. We also did some optimizations in terms of the set of operations we use, mainly by using a group in our features in groups of 8, and we could use like AVX and neon instructions. This part also of the design of the network is a combination of the design. And now, so as I said in the video part, we have a BaseNet, which is very low compute, and we have HyphenNet, which produces better facts. And with these two and a combination of how often we run these networks, we support 4 LOD levels. In LOD 4, in the highest LOD, we run the encoder of HyphenNet, of BaseNet, and all the decoders at 30 FPS, and the facts produced are coming from HyphenNet. And for instance, like in a very low-end device, this can be a Samsung S6 from 2015, this runs in 14 milliseconds on average. Well, I mean, average and on per frame, because we run every network at the same FPS. Now we can go to LOD3, in which we run HyphenNet, but we run it at 15 FPS, but we still produce results at 30 FPS by running the decoder twice, so running it at 30 FPS, and we reuse the feature predicted on the previous frame, so run only at 15 FPS from the encoder. And then we go under 10 milliseconds in the Samsung. If we go to LOD2, we still run the 3 networks, and in this case, so the 2 HyphenNet and BaseNet, and in this case also BaseNet, we run it at 15 FPS. There maybe most of the loss is a little on the dynamics of the head pose. And then in the lowest quality LOD1, we just run BaseNet, we run it at 15 FPS, but we produce outputs at 30 FPS. And there we can go under 4 milliseconds. on a very low-end device. The results here is just a glimpse of how the results differ from LODs. LOD1 is mainly different than the others because it uses a different network and has been trained also with different dynamics because it's, to make it more robust, tends to be like lower frequency or, but otherwise, like the subsampling, the changing of the FPS doesn't have so much effect. We did some ablation study, small ablation study on the video decoder. The baseline, which is not what we have in the product, but it would be just using non-temporal, just using a fully connected layers and no temporal losses, no temporal architecture. The second case is the one I described. We use temporal causal convolutions, means we only use like present and past frames. And then we use a third one where we use the same architecture, but we use a frame from the future. Basically, you can see in the paper, but the error in terms of positional error is the same on the three architectures. But then the jitter, we have a jitter metric, and the jitter is there's a high reduction from jitter from the non-temporal to the temporal one, and a slightly more on the non-temporal one. We can see here, for instance, so left is the non-temporal network, right is the temporal one, and you can see this high frequency, especially when there are occlusions, and so if you don't use. So one of the things is by using this temporal architecture on the decoder allow us to have a very, very small network or encoder. So it's like they benefit one from the other. Finally, we did a comparison with AirKit. So AirKit is the library from Apple. It's the only one we could compare because it's the only one that produces facts and that we could compare one-to-one. Our system can run on any device as opposed to AirKit that needs iPhone 10 or iPhone X above. And the animations are similar in terms of quality. In some things we are better, some things they are better. But in general, or like in two specific cases, we believe we are better. One is jitter in self-occlusions and side occlusions, and the other is like we produce, like on side views and self-occlusions, we produce, I would say, like more symmetric outputs. So we tend, like when you don't see, so when you don't see part of the face, our network imagines like a more symmetric, which tends to be more pleasant. Yeah, and I believe that's all. Thank you.